What if Mars wasn't just a barren, lifeless planet? What if beneath its dusty surface lies evidence that the red planet once hosted complex life, billions of years ago? NASA's Perseverance rover may have uncovered groundbreaking signs: complex organic molecules, layered biofilms, and chemical patterns suggesting a diverse ancient biosphere. Could this mean life is not unique to Earth, and that the universe is far more alive than we ever imagined? Join us as we explore these historic discoveries that could rewrite everything we know about our neighboring planet and the very nature of life itself. NASA's Perseverance rover made a historic landing in the Jezero Crater, a sprawling depression on Mars that scientists believe was once home to a vast lake. The rover's mission is ambitious and groundbreaking: to search for definitive signs of past life on the red planet and to collect rock and soil samples that could one day be returned to Earth for detailed laboratory analysis. This mission is the first step in a multi-billion-dollar plan to not just explore Mars remotely, but to bring pieces of it home, allowing scientists to study Martian geology and chemistry in ways that no rover instrument could fully accomplish. From the moment it touched down, Perseverance began a meticulous campaign of exploration. It navigates the rugged Martian terrain with a combination of autonomous systems and human guidance, capturing high-resolution images of rocks, cliffs, and sediment layers that hold the secrets of Mars's past. The rover is equipped with specialized instruments designed to drill into the surface, extract core samples, and analyze them on the spot using chemical and spectroscopic techniques. Each action is deliberate and carefully planned, as the rover must preserve the integrity of the samples while operating in one of the harshest environments in the solar system. Jezero Crater itself is a remarkable site for exploration. Billions of years ago, it is believed to have hosted a river delta that deposited layers of sediment over time, creating a natural archive of the planet's history. Scientists chose this location because deltas on Earth are among the richest sites for preserving organic molecules and microbial life. By studying the layers of sediment in Jezero, Perseverance has the opportunity to uncover evidence of ancient water, chemical reactions, and potentially the earliest forms of life on Mars. As the rover moves through the crater, every photograph, every drill core, and every chemical analysis contributes to a larger picture of Mars's past. Its mobility allows it to traverse rocks, ridges, and crater floors that were previously inaccessible, enabling the study of areas that might hold the best preserved evidence of past habitability. Perseverance is not simply a machine moving across a barren landscape. It is a sophisticated laboratory on wheels, methodically unlocking the secrets of a world that has been silent for billions of years. Beyond the science, the mission carries profound implications for humanity. By exploring Mars and searching for traces of ancient life, Perseverance helps answer some of the most fundamental questions about our place in the universe. Was life unique to Earth, or could it arise elsewhere under the right conditions? Could Mars, once wet and chemically active, have hosted life forms that followed a path entirely independent of our own? Every maneuver the rover makes, every layer of rock it examines, brings humanity closer to understanding not just the history of a distant planet, but the potential for life throughout the cosmos. In essence, Perseverance is not just exploring Mars. It is opening a window into a chapter of planetary history that has been hidden for eons. Each rock it touches and every sample it collects is a clue in a story billions of years in the making. As it begins its mission, the world watches, knowing that the discoveries made in Jezero Crater could forever change the way we understand life, planets, and the universe itself. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. As Perseverance continued its carefully planned mission across the Jezero Crater, the rover entered a region labeled Sector Delta 9. What initially seemed like a routine section of clay-rich sediment would soon reveal one of the most astonishing discoveries in the history of planetary science. During a standard subsurface drilling operation, the rover's instruments extracted core samples that at first glance appeared ordinary. But as the data began to stream back to mission control, scientists quickly realized that this was no typical Martian soil. The samples contained complex organic macromolecules, intricate carbon chains arranged in repeating patterns that immediately caught the attention of chemists and astrobiologists. These structures were far beyond the simple amino acids, small hydrocarbons, or random organic compounds that had been detected in previous missions. The molecular arrangements suggested a level of sophistication consistent with precursors to DNA or RNA, the fundamental building blocks of life on Earth. This was a moment of profound excitement. The rover had not simply detected traces of chemistry. It had uncovered signatures that hinted at the possibility of past biological processes. The discovery challenged decades of assumptions about the red planet. Organic molecules had been found before, but these were different. Their complexity, symmetry, and organization implied processes that were more than random chemical reactions. On Earth, similar molecules are the product of enzymatic activity, or biological synthesis, raising the tantalizing possibility that Mars may have once hosted life, or at least conditions capable of supporting lifelike chemistry. Adding to the significance was the location and depth at which these molecules were found. Buried meters beneath the surface, they had been shielded from cosmic radiation, oxidizing agents, and the harsh Martian environment for potentially billions of years. This indicated that the molecules were not recent or transient, but ancient and stable, preserved like messages in a geological time capsule. Scientists could immediately rule out contamination from Earth. The rover's drill was sterilized before launch, and the layers containing these molecules were isolated from the surface, making a native Martian origin almost certain. The implications of this finding were enormous. If these molecules were indeed a product of biological or bio-like processes, it suggested that Mars had once possessed the right combination of water, energy, and chemical ingredients to support life. The discovery transformed Sector Delta 9 from an ordinary patch of Martian dirt into a treasure trove of cosmic history, potentially holding the keys to understanding how life can emerge beyond Earth. The excitement in mission control was palpable. Data from the rover's spectrometers, ultraviolet sensors, and Raman instruments confirmed the presence of these macromolecules, and repeated scans showed consistent results. This was not a one-off anomaly or instrument error. Mars had just revealed a hidden chapter of its past, written in the language of chemistry, encoded deep within rocks that had lain undisturbed for eons. As scientists began to analyze the structures in detail, the magnitude of the discovery became clear. These were not random organic compounds. They were organized, patterned, and complex, properties that on Earth are indicative of life or lifelike chemical processes. Every measurement, every spectrum, every image reinforced the sense that Mars was more than a barren desert. It was a planet that, in its ancient past, had the capacity to generate molecular complexity on par with the earliest biological systems on Earth. This unexpected molecular discovery marked a turning point in the mission. Perseverance was no longer simply cataloging rocks and dust. It had begun to uncover the very chemical fingerprints of a world that may have once been alive. The implications stretched beyond Mars, beyond our solar system, and into the fundamental questions of whether life is a rare accident or an inevitable outcome of chemistry when conditions allow. The moment Perseverance's instruments detected the complex organic molecules, scientists knew they had stumbled upon something extraordinary. But the next revelation made the discovery even more profound. These molecules were not scattered across the surface, where they could have been contaminated by cosmic dust, meteorites, or even earthly debris. They were buried meters beneath the Martian surface, safely tucked away in the planet's ancient geological layers. This depth was critical because it provided natural shielding from cosmic radiation, ultraviolet rays, and the harsh, oxidizing environment that dominates Mars today. Within these layers, the molecules were encased in mineral formations of olivine and serpentine, creating what scientists now refer to as natural time capsules. These mineral pockets acted like protective vaults, preserving the molecular structures for possibly billions of years. They were untouched by erosion, wind, or chemical weathering, meaning the signatures found were pristine, undisturbed relics of Mars' deep past. For researchers, this preservation was like finding a message in a bottle, delivered from a world that had been silent for eons. The implications of these protective layers were staggering. On Earth, similar preservation occurs in deep sediments or rocks that have been shielded from surface processes, keeping organic compounds intact over geological time. On Mars, these time capsules meant that the molecules discovered by Perseverance were not a modern anomaly. They were ancient, original, and unequivocally Martian. The rover's carefully sterilized drill and the mission's stringent contamination protocols ruled out any chance that these compounds had arrived from Earth. The molecules were native to Mars, a genuine record of the planet's early chemical environment. This discovery changed the way scientists viewed the Martian subsurface. No longer was it simply a barren layer of rock and dust. It became a repository of Mars' chemical and potentially biological history. The layers where these molecules were found suggested a stable environment capable of preserving delicate chemical structures over unimaginable spans of time. The combination of olivine and serpentine minerals provided both mechanical protection and a chemically favorable environment that could prevent the breakdown of complex organic molecules. Beyond preservation, the depth and context of these molecules told a story about the planet itself. They suggested that Mars had been capable of sustaining complex chemical reactions in a relatively stable environment long before the surface became the dry, irradiated desert we see today. For scientists, this was a powerful clue. Mars's past was not just geologically active, but chemically rich, creating the conditions necessary for lifelike processes to emerge and persist. The realization that these molecules were ancient and indigenous shifted the focus of the mission. Perseverance was no longer just exploring a crater. It was unlocking a historical record of a planet's biochemical potential. Each mineral-encased sample became a window into Mars' distant past, a past in which the planet may have nurtured the building blocks of life in hidden, protected niches. As the rover continued its work, scientists began to understand the significance of these time capsules. They were more than just rock. They were archives of Martian history, preserving chemical evidence of a world that may have been biologically expressive. This discovery not only confirmed that Mars had complex organic chemistry long ago, but also hinted at the possibility that life, or lifelike processes, could have arisen independently on a neighboring planet in our solar system. The ancient and indigenous nature of these molecules elevated the mission from exploration to revelation. What Perseverance had uncovered was not a fleeting signal or a surface anomaly. It was a direct connection to the planet's distant history, a testament to Mars's potential as a cradle for life, and a discovery that would reshape our understanding of where and how life could exist in the universe. The discovery of these complex molecules was remarkable on its own, but the analysis revealed something even more astonishing. Detailed examination of the molecular structures showed patterns that went beyond simple chemistry. They exhibited symmetry, repeating sequences, and polymer complexity, characteristics that, on Earth, are hallmarks of biological synthesis or enzymatic catalysis. In other words, these molecules were organized in a way that suggested intentional assembly, rather than random chemical reactions. Such patterns are rarely formed through purely abiotic processes. On Earth, symmetrical and repeating structures are often the product of life's machinery, from enzymes to DNA replication systems. The fact that similar molecular traits were found on Mars raised the possibility that, at some point in its history, the planet had conditions capable of supporting lifelike processes. These were not isolated molecules randomly scattered across the Martian soil. They were coherent, intricately structured compounds, preserved in a stable environment for billions of years, suggesting that the chemistry of Mars was not only complex, but also guided by specific processes that mimic biological behavior. The preservation of these molecules was equally compelling. Despite billions of years of cosmic radiation, surface erosion, and temperature fluctuations, the molecules retained their structural integrity. This indicated that Mars once had regions where water, minerals, and chemical energy were present in a delicate balance, enough to support processes that could assemble complex molecules with lifelike properties. The olivine and serpentine mineral matrices acted as natural shields, protecting these molecular structures from degradation and preserving them as snapshots of Mars's ancient chemistry. Scientists analyzing the data noticed repeating polymer sequences, similar to short segments of RNA or DNA. While not identical to Earth's genetic material, these sequences showed clear signs of ordered construction and replication potential. It suggested that early Mars may have hosted molecular networks capable of self-organization, a critical step toward the emergence of life. These molecules were more than chemical curiosities. They were evidence that Mars' environment could foster processes that on Earth lead directly to biology. Moreover, the combination of molecular complexity and environmental stability indicated that Mars was not a passive backdrop, but an active participant in chemical evolution. Mineral surfaces, chemical gradients, and subsurface water pockets likely facilitated reactions that selectively promoted the formation of these organized molecules. This scenario paints a picture of Mars as a planet with localized niches where prebiotic chemistry or even early lifelike systems could flourish, shielded from the harsh conditions that dominate its surface today. The discovery forced scientists to rethink long-held assumptions. Life, or at least lifelike chemical systems, might not be unique to Earth. Mars demonstrated that with the right conditions, water, energy, and protective minerals, complex molecular structures capable of mimicking biological behavior can emerge. These findings brought the world closer to answering one of humanity's most profound questions. Is life a singular occurrence or a natural outcome of chemistry under the right conditions? In the end, the molecular evidence from Sector Delta 9 provided a tantalizing glimpse into a time when Mars may have been chemically alive. It hinted at processes that, while not necessarily producing organisms as we know them, demonstrated that the building blocks of life could emerge independently on another world. This discovery marked a pivotal moment in the exploration of Mars, shifting the mission from geological investigation to a direct search for the fundamental signatures of life beyond Earth. As Perseverance continued its meticulous investigation of the Martian subsurface, its high-resolution imaging systems captured something that sent ripples through the scientific community. Embedded within the mineral-rich layers of Sector Delta 9, the rover observed microscopic structures that were astonishingly intricate. These formations displayed fractal branching and filamentary patterns, strikingly similar to microbial mats found in Earth's extreme environment, such as hydrothermal vents, acidic hot springs, and arid desert crusts. While no living organisms were detected, these structures acted like molecular footprints, fossilized imprints left behind by ancient biological activity. On Earth, microbial mats create distinctive patterns as colonies grow, interact, and leave behind mineralized remnants once the life forms die or move on. The Martian patterns mirrored this behavior with remarkable fidelity, suggesting that billions of years ago, similar processes could have been occurring on Mars. These microscopic formations were not random cracks or mineral deposits. They bore the hallmarks of organized, lifelike activity preserved over eons. The context of their preservation added to the significance. Encased within olivine and serpentine minerals, these microscopic imprints had been shielded from radiation, chemical oxidation, and the harsh Martian surface environment. This protection allowed the structures to maintain their complexity and clarity, giving scientists a nearly pristine window into ancient Martian chemistry and potential biology. It was as if the planet itself had curated a time capsule, holding a record of chemical and possibly biological interactions that predated the surface becoming inhospitable. Further analysis revealed that the spatial organization of these structures was consistent with energy-driven chemical processes that are typical of early microbial communities on Earth. The fractal nature and connectivity of the filaments suggested replication or growth patterns, indicating that these formations were more than simple mineral artifacts. They were imprints of processes that could have been guided by early lifelike activity. In other words, Mars had left behind a molecular memory of its ancient environment, encoded in patterns that mirrored those produced by life on Earth. The discovery was profound because it provided tangible visual evidence of processes that might have been biological in origin. Even without detecting living cells, the combination of complex molecular structures, preserved mineral matrices, and fractal microscopic patterns painted a compelling picture. Mars once hosted conditions suitable for sustaining chemical networks or microbial systems capable of growth, replication, and pattern formation. These imprints offered a new kind of evidence, complementing the chemical signatures found in the core sample, and providing multiple lines of support for the idea that life, or lifelike chemistry, was once possible on the red planet. This microscopic evidence transformed our understanding of Mars. It was no longer a world defined solely by its barren deserts and dusty plains. Beneath its surface lay a hidden record of chemical complexity, preserved patterns, and potential biological activity. Perseverance had not only revealed traces of ancient molecules, but had also uncovered the fossilized imprints of processes that may have been the precursors to life itself. The mission had begun to unlock a story written in the smallest details, a story of a planet that was once chemically vibrant and perhaps biologically active, billions of years before humans ever looked up at its reddish glow in the night sky. Astrobiology scientists continued analyzing the molecular data from Sector Delta 9. A groundbreaking realization emerged. While the complex organic molecules shared characteristics with Earth's biomolecules, closer inspection revealed key structural differences. The Martian compounds exhibited unique chirality, unusual bonding angles, and functional groups that do not typically appear in terrestrial chemistry. These distinctions suggested that the molecules were not simply contaminations from Earth, nor were they identical copies of familiar biomolecules. Instead, they represented an independent biochemical system, one that had evolved under Mars' unique environmental conditions. Chirality, the handedness of molecules, is a particularly striking indicator. On Earth, life almost exclusively uses left-handed amino acids and right-handed sugars. The Martian molecules, however, showed a mixture of left and right-handed forms in organized patterns, implying that Mars developed its own rules for molecular assembly. These differences extended to bonding angles and functional group arrangements, which affected how the molecules folded, connected, and reacted. Essentially, these molecules were alien in their chemistry, yet they demonstrated the same principles of organization, replication, and complexity that underpin lifelike processes. This discovery had profound implications. It suggested that life, or at least lifelike chemistry, is not unique to Earth. Within the same solar system, Mars had generated molecular systems that could mimic fundamental biological function independently. This concept of parallel biochemical evolution challenges the long-held assumption that life follows a single universal template. Instead, it supports the idea that under suitable conditions, chemistry naturally tends toward complexity, organization, and even prebiotic or biogenic patterns. The notion of independent biochemical evolution also reframes our search for life. Beyond Earth, it implies that life could arise in diverse forms, shaped by the unique conditions of each planet. Mars's molecules, preserved in ancient mineral time capsules, represent a second experiment in lifelike chemistry conducted by nature within our cosmic neighborhood. This parallel system is evidence that the emergence of life, or lifelike chemical processes, is not a one-off occurrence, but a potential natural outcome whenever conditions permit. Furthermore, the differences between Martian and terrestrial molecules provide a roadmap for identifying alien biochemistry in future missions. Scientists can now look for chirality patterns, bonding variations, and functional group arrangements that deviate from Earth norms as potential indicators of independent life or prebiotic processes. In other words, Mars has given us a blueprint for recognizing life in forms we might not have expected. The discovery underscored a profound truth. The universe may be more hospitable to life than previously imagined. Earth is not necessarily the singular cradle of biology in our solar system. Mars, long considered barren, may have conducted its own evolutionary experiment, producing complex, organized molecules capable of mimicking life processes. This independent, biochemical evolution opens new horizons for understanding how life emerges, how it adapts to different planetary environments, and how widespread life might truly be in the cosmos. With this realization, Perseverance's mission transcended exploration. It became a direct probe into one of humanity's deepest questions: can life emerge independently on multiple worlds? The molecules of Sector Delta 9 had answered, in their own intricate, silent way, that the chemistry of life is not confined to Earth alone. It can arise wherever the conditions are right. While the molecular discoveries in Sector Delta 9 were groundbreaking on their own, understanding the environment that produced and preserved them was equally critical. Perseverance's observations of Jezero Crater revealed a remarkably detailed geochemical and environmental record. The crater's sedimentary layers, visible in cross-sections of exposed rock, told a story of repeated deposition by water, indicating that Jezero was once a stable, lake-like environment rather than a transient or seasonal pond. Ripple patterns etched into ancient sediments suggested persistent water currents, while stratified deposits indicated cycles of sedimentation over long periods. These features implied that liquid water was present for extended times, creating a stable environment that could facilitate complex chemical reactions. Such conditions would allow molecules to form, interact, and accumulate in ways impossible on today's cold, dry surface. Further analysis revealed alterations in clay minerals, evidence that water-rock interactions had chemically modified the sediments over millions of years. Clays are particularly important because they can absorb organic molecules, protect them from degradation, and even catalyze reactions that form larger, more complex structures. These altered minerals served as both a cradle and a shield, nurturing chemical evolution while preserving its products over geological timescales. Hydrothermal mineral deposits found in certain layers added another dimension to this picture. Hydrothermal activity produces chemical gradients and localized energy sources, essential ingredients for lifelike processes. The combination of warm water, mineral-rich sediments, and chemical gradients created microenvironments where complex, organic molecules could assemble, stabilize, and even exhibit patterns reminiscent of primitive metabolism. In essence, Jezero Crater was not just a passive repository of molecules. It was an active, dynamic system that provided the necessary environmental context for molecular complexity. The interaction of water, minerals, and chemical energy created pockets of stability that allowed Martian chemistry to flourish, producing the molecules and structures that Perseverance now examines billions of years later. This geochemical context also strengthens the argument that the complex molecules were indigenous and potentially biogenic. They were not random deposits. They were formed, modified, and preserved within an environment conducive to complex chemistry. Jezero Crater, once warm and water-rich, acted as a natural laboratory where the fundamental components for lifelike processes could emerge, interact, and leave behind the signatures that scientists are now uncovering. By connecting the molecular evidence with the broader environmental story, Perseverance paints a vivid picture of ancient Mars, a planet with lakes, flowing water, reactive sediments, and energy-rich minerals, a world with the conditions necessary to support the formation and preservation of complex organic chemistry. This geochemical and environmental context transforms Jezero from a dry, barren landscape into a window on a past where Mars may have been chemically and biologically active, offering compelling clues about the planet's potential to host life. Perseverance's discoveries went beyond molecular structures and microscopic patterns. The rover's instruments also detected subtle isotopic signatures and seasonal atmospheric phenomena that hinted at past biochemical activity. Measurements revealed light isotopes of nitrogen and sulfur in the Martian rocks, isotopic ratios that are difficult to produce through purely abiotic chemical reactions. On Earth, such isotopic patterns are often the result of selective biochemical processes, where living systems preferentially incorporate lighter isotopes into their molecules. Adding to the intrigue, Perseverance observed recurring seasonal methane emissions in the vicinity of Jezero Crater. Methane on Mars is unstable in the atmosphere, breaking down relatively quickly under ultraviolet radiation. Its periodic reappearance suggests an active source, either chemical or potentially biological, continuing to release gas over time. The combination of isotopic evidence and methane emissions strengthens the case for processes that resemble early lifelike chemistry or even intermittent microbial activity beneath the surface. Even the molecular chirality offered subtle hints. While not identical to Earth's biomolecules, the Martian compounds displayed a slight preference for one orientation over its mirror image. Such selective chirality is rarely random. It often emerges from chemical processes influenced by environmental or biological factors. This preference, preserved over billions of years, aligns with the broader picture of complex molecular evolution on Mars. Radar scans of the subsurface revealed additional surprises. Anomalous cavities and chambers were detected beneath the sediment layers, some large enough to have sheltered microbial colonies or water pockets shielded from radiation. These protected niches could have provided the ideal conditions for organic molecules to assemble, interact, and even persist for extended periods. The combination of geochemical, isotopic, and structural evidence paints a coherent story. Mars once had stable microenvironments where lifelike processes could occur, possibly in ways analogous to early Earth. Taken together, these findings suggest a world that was not merely chemically active, but potentially biochemically selective. Light isotopes, molecular chirality preferences, methane cycles, and subsurface shelters all point toward processes that resemble life, or at least the molecular precursors of it. Perseverance had uncovered not just static evidence, but dynamic signatures of a planet that may have been capable of sustaining primitive biochemical systems. This body of evidence challenges our assumptions about Mars as a barren world. It indicates that beneath its surface lies a hidden record of chemical evolution, environmental stability, and even potential microbial refuges. Each new data point brings scientists closer to understanding whether Mars ever hosted life, and if so, what forms it might have taken. The implications for astrobiology are profound, raising the possibility that life, or lifelike chemistry, has emerged independently on multiple worlds within our solar system. As Perseverance continued its detailed survey of Jezero Crater, scientists uncovered signs that the Martian environment may have been more biologically diverse than previously imagined. Microlaminations within sedimentary rocks revealed finely layered structures, each layer potentially representing different periods of chemical activity or microbial influence. These thin, repeated bands are reminiscent of stromatolites on Earth, where successive microbial mats build distinct layers over time, preserving a record of environmental and biological interactions. In addition to microlaminations, the rover detected evidence of layered biofilms, thin, sheet-like structures formed by colonies of microorganisms interacting with their mineral surroundings. On Earth, biofilms serve as protective communities that stabilize chemical gradients, concentrate nutrients, and facilitate collective biochemical activity. The presence of analogous structures on Mars suggests that if life, or lifelike chemistry, existed, it was capable of forming organized cooperative systems even without developing complex multicellular organisms. Regional chemical diversity further supports the idea of a complex biosphere. Variations in organic molecule types, isotopic signatures, and mineral associations across different sections of the crater imply that multiple biochemical systems coexisted, each adapting to localized environmental conditions. Some regions appear to have favored molecules with certain chirality or functional groups, while nearby areas show different molecular preferences, hinting at a landscape of chemical specialization. Together, these observations suggest rapid evolutionary adaptation to fluctuating Martian environments. Even in the absence of multicellular life, primitive biochemical systems may have diversified, exploiting niches within the crater's sediments and mineral-rich layers. The evidence points to a dynamic and heterogeneous Martian biosphere, where molecular networks evolved, interacted, and persisted under varying chemical and physical conditions. The implication is profound. Mars may not have hosted a single type of prebiotic chemistry, but a mosaic of coexisting systems, each capable of independent chemical evolution. These findings challenge the notion of a uniform, barren Mars and open the possibility that lifelike chemistry, and perhaps primitive life itself, could have been far more widespread and resilient than previously considered. By examining these complex and layered signatures, scientists gain a glimpse into an ancient Martian biosphere, one that was diverse, adaptable, and sophisticated on a microscopic scale. Perseverance has uncovered not just isolated molecules or structures, but an entire chemical ecosystem preserved over billions of years, reshaping our understanding of what Mars once was and what it might still hold beneath its surface. The discoveries in Jezero Crater go far beyond the excitement of finding complex molecules or fossil-like structures. They strike at the very heart of humanity's understanding of life, its origins, and its place in the universe. For centuries, life was considered a phenomenon unique to Earth, a delicate accident in the vast cosmic expanse. The Perseverance findings challenge this Earth-centric perspective. Evidence of complex, independent biochemical systems on Mars suggests that life, or at least lifelike chemistry, may not be rare. Instead, it could be a natural consequence of planetary chemistry. Whenever conditions are favorable, this revelation has profound scientific implications. Astrobiologists now have direct evidence that independent chemical evolution can occur in our own solar system, providing a blueprint for identifying life beyond Earth. Exoplanet studies, previously speculative, now gain context. If Mars and Earth each fostered complex biochemical systems under the right conditions, then planets around other stars could similarly host diverse prebiotic or biotic chemistry. The universe may be more biologically active than humanity ever imagined. Philosophically, the discovery forces a re-evaluation of humanity's perceived uniqueness. For millennia, life on Earth has been regarded as singular and precious. Mars demonstrates that the emergence of life, or lifelike chemistry, is not exclusive to our planet. This challenges long-held assumptions about life as a solitary phenomenon and opens the door to the possibility that the cosmos could be teeming with independent experiments in biology, each shaped by its own planetary environment. Ethically, these findings raise urgent questions about planetary protection and human exploration. If Mars preserves traces, or even remnants, of independent biochemical systems, future missions must carefully consider contamination risks. Introducing Earth microbes could disrupt or destroy Martian chemical ecosystems that have persisted for billions of years. Humanity faces a responsibility to explore with caution, preserving the integrity of alien biochemistry while continuing scientific inquiry. Ultimately, the Jezero discoveries compel humanity to reconsider its role in the cosmos. Life may not be an isolated miracle, but a common outcome of chemistry interacting with the right environment. The universe could host countless independent biospheres, each with its own story of emergence, adaptation, and evolution. As we stand on the threshold of interplanetary exploration, these findings demand humility, curiosity, and ethical foresight. Perseverance has not merely expanded our knowledge of Mars, it has expanded our understanding of life itself. It challenges us to imagine a universe where life is abundant, diverse, and resilient, and it compels us to approach exploration not as conquerors, but as stewards of a cosmos that may be far richer and more alive than we ever dreamed. Perseverance has revealed a Mars far more complex and dynamic than we ever imagined, a world where chemistry teetered on the edge of life, and perhaps even crossed it. From ancient molecular structures to signs of diverse biochemical systems, these discoveries challenge everything we thought about life's uniqueness and resilience. As we continue exploring, Mars reminds us that the universe may be alive in ways we are only beginning to understand, inviting humanity to approach it with both wonder and responsibility. If you found this journey through hidden science, cosmic secrets, and potential alien infrastructure as mind-blowing as we did, make sure to subscribe and hit the notification bell. Don't miss future explorations into the universe's deepest mysteries, because some secrets are just waiting to be uncovered.